Hello everyone. In this set of videos we're going to talk about regression inference. This will be all about how to use a sample and a regression that we run on a sample to draw some conclusions about the overall population. We're going to talk about two different interpretations of regression and the assumptions that we need to be in place to make those interpretations. We're also going to be talking about how to do hypothesis tests. As with the last set of videos, we're going to be using the demand Excel file. I encourage you to load that up to follow along. In this first video, we are going to draw the distinction between correlational and causal regressions, and then get into what makes a correlational regression. To start out, we need to think about what is the difference between correlation and causality. Correlation means that we have variables that tend to move together. It doesn't imply anything more than that. One of the variables could be the driver of the change in the other, or we could have some third variable that's getting involved that is causing both the change. We don't know, and we're not making any claim to know. If we claim that there is a causal relationship, we're saying that a change in one variable directly causes a change in the other. Variables with a causal relationship also have a correlational relationship, but it's not necessarily always going to go the other way around. This leads us to thinking about two different interpretations of a regression. The techniques for running the regression are exactly the same as we covered in the last set of videos, but the interpretation is very different and the assumptions that we need are also very different. The distinction between these two interpretations is very important because we need to be able to know what we can and can't do with our regression. In general, correlation is much easier to show and requires much weaker assumptions than a causal interpretation. But going along with that, what we're able to do with it is a bit more limited. If our interpretation of our regression model is correlational only, that's going to be enough for us to predict outcomes in our dependent variable based on known values of the explanatory variables, but that's as far as we can go with it. We can't actually say if we change one of these explanatory variables, then we can predict a change in the outcome. All we're saying is that they tend to go together. We'll talk about what we need to establish causality in a coming video. For now, let's talk about a regression for correlation. The underlying assumption of a regression for correlation is that we have a population that if we had all of the data in the population, then we could run a regression with all of that data, probably a huge amount of data, and we could get some regression coefficients out of that. Now, in reality, we can't actually see the population. Say the population is the entire population of the United States. That's hundreds of millions of people that we just can't get access to. So what we have to do is the next best thing, which is to take a randomly selected sample. As before, we're going to have a sample of size n, and for each observation in the sample, we have a value for our dependent variable y. We'll call that yi for observation I, but then we're also going to have an x1, an x2, an x3, all the way out to xk, k being our total number of variables. For each observation, we're going to have a value for each of those. When we run the regression using our sample as opposed to the population, that's going to give us estimates of our parameters. Those are our beta hats. If we had the entire population and ran a regression with that, then we would know the true betas in the population. But we don't, and so we're going to use our sample and use our beta hats instead. One way that we can assess whether our beta hats are actually good estimates of the true betas in the population is to think about the property of consistency. We have consistent estimators if they converge to the true population parameters as the sample size increases. This assumes that we have a random sample, and if we do, then as the sample size n gets bigger and closer and closer and closer to the true population size, then those beta hats are going to get closer and closer and closer to the true betas from the population. Now, as our sample gets bigger, eventually our sample could encompass the entire population, then of course our beta hats would be our true betas. To give a visual illustration of how a correlational regression works, I've drawn two graphs. On the left, we have a graph of the population. The population is something that, as data analysts, we don't actually ever see, but we do know that it's out there somewhere. Each of the green dots that you see in the picture are members of the population. The variables y and x here have some relationship with each other in that population. I'm going to draw in a regression line. This is the true regression line in the population. It has an intercept of beta naught, and it has a slope of beta 1. For each of our members of the population, the distance between that dot and the regression line is the epsilon, or error, for each of those points. And each one has their own unique epsilon that shows us how far it departs from the regression line. The equation for y is going to be y equals beta naught plus beta 1x. That's going to get us the blue line. And then plus epsilon. Of course, we don't actually have every single one of those green dots. We have a subset of those, and that's our sample. Imagine that each of these red dots over here are also represented in these green dots, but not all the green dots come over here as red dots. So we just have n red dots out of the total number of green dots. When we run the regression over here, we're also going to get a line. But instead of an intercept of beta naught, we're going to have an intercept of beta naught hat, and we're going to have a slope of beta 1 hat. Hopefully our beta naught hat will be pretty close to beta naught, and our beta 1 hat will be pretty close to beta 1, but it's not going to be exactly there, and we won't ever know exactly how far away it is. It's just our best guess as to what our true betas are, given the information that we do have, our sample. And if we take one of these red dots, let's say this one right here, let's call that dot observation 1. The height of that observation, that's y1, and the distance on the x-axis is going to be x1. And when we plug in any of our x's into our estimated equation, that's going to tell us what our y hat is going to be. So remember that y hat is beta naught hat plus beta 1 hat times x. So that's going to tell us where exactly along the regression line we are. So this height right here, that's going to be y1 hat, and then the distance between these two, that's going to be e1, the residual. Remember from the previous set of videos that ei equals yi minus yi hat. And that some of those e's are going to be positive, some of them are going to be negative. Now, if we think about what happens as if we think about what is going to happen as n gets bigger, we're going to get more and more red dots coming over here from the green dots. And eventually, we're going to get closer and closer and closer, and our sample is going to look more and more and more like the real population. As we add new red dots, this blue line is going to adjust slightly, and as n gets larger and larger and larger, closer to the true population size, those lines are going to get closer and closer and closer to each other, and that's what we mean by consistency. Ultimately, where we're going with this is to do some hypothesis tests, but to get there, we need to think about what is the distribution of our estimates. I mentioned earlier that because our samples are selected randomly, we're going to get slightly different estimates for any given sample. And this is where the central limit theorem comes in. The CLT tells us the probability distribution of our estimates. The central limit theorem says that any of our beta hats are normally distributed with a mean of beta, the true value, and a standard deviation of sigma. When I write beta j here, j is just standing in for any of the parameters that we're trying to estimate. If we have 3 different parameters, j could be 1, it could be 2, it could be 3, or 0, of course, for the intercept. The central limit theorem hinges on the idea that we have a sufficiently large sample size. The interesting thing about this is that it does not actually matter what the distribution of the actual observations are. As long as we have a sufficiently large sample size, the estimates will be normally distributed. So now you might be wondering, what do we mean by sufficiently large? You might have heard in a stats class before that sufficiently large usually means about 30 observations. And in a basic stats class, that's sufficient, but what we really need is about 30 observations for each parameter that we're trying to estimate. So if you're only estimating one thing, 30 is good enough. But we are estimating in a regression multiple things. If we go back to our equation here, we're estimating beta naught, we're estimating beta 1, beta 2, beta 3, all the way up to beta k. So we have k parameters to estimate for k variables, plus one more for the intercept. So what we're going to need to apply the CLT is to have n at least as big as 30 times k plus 1, where k is the number of explanatory variables we have, and the 1 is there for our intercept term, our beta naught. Let's briefly come back to this concept of why are the estimates randomly distributed? Intuitively, it's because the samples are random. So every time you pull a new sample with different members of the population coming in, we're going to get slightly different estimates. So I want to illustrate how this works over in Excel. In a previous video, we ran a simple regression of quantity on price using our data 1 sample. We got an intercept estimate of 4,279 and a slope estimate of negative 9.5. Now I want you to go to this tab right here that says data 2. You can see it looks very similar to data 1, except that now I've simply drawn a new sample. What we'll do now is run the exact same regression, quantity on price, but using this new data set. We'll go over here to data analysis, click regression, and select our quantity as the y, and then we will select price as the x. Again, make sure we've got label selected and click OK. You can see here that we have a substantially different estimate for both the intercept and for the slope. I've also included in this file a tab right here that says DGP. This is the actual data generating process that I use to create this data. You can see on this sheet that I have px, py, and m selected randomly, as well as a randomly generated epsilon that I then use to build the quantity. You can think about this sheet as our population. Press F9 a few times, and you can see the sheet recalculate, and you can just create more samples like that. And that's all I did to make data 1 and data 2. If we were to run the regression with the randomly generated set that I just made, it's going to have a different result than both of the ones that we already did. This is meant to simulate the effect of repeated sampling from a population and randomly selecting different members of that population every time. As I discussed earlier, our estimates, the beta hats, are normally distributed with a mean of beta and a standard deviation of sigma. We can't use this distribution, though, because we don't actually know what beta and sigma are. Those exist in the population, and anything that's in the population we can't see because we don't have access to the full population. The solution to this is that we are going to estimate them. Of course, we've already estimated beta, and our estimate for that is beta hat, but what about sigma? For this, we're going to need something new, and that's what we call the standard error. Each of our beta hat j's will have its own standard error unique to that estimate. You can think of the standard error as a measure of how precise our estimates are. The short answer to how to calculate the standard error is to find it in the regression table. I'm back in Excel looking at our original regression using data 1. To the right of the coefficients, we can see a column in the table that says standard error, and these are the standard errors for each of our estimates. Beta naught hat is 4,279, and the standard error of beta naught hat is 284. Beta 1 hat is negative 9.5, and the standard error of beta 1 hat is 1.38. Now the long answer is that there is a formula that we can use to calculate standard error. It is a bit complex and outside the scope of what we're doing here in this video, but for completeness, I'm going to give you the formula. The one thing I do want you to take away from this formula is that we have in the denominator an n here. That means that when n gets bigger, the standard error of all the beta hats is going to come down. So the larger the sample size, the smaller the standard errors. The actual standard error calculation doesn't add a whole lot to our understanding, so we're going to let Excel handle it. Let's talk a little bit about what the standard error is and what it does for us. As I mentioned before, the standard error is a measurement of how precise our beta hats are. What does that mean? Recall that when I repeatedly sampled our data, I got different estimates in the regression every time. The standard error is going to tell us how much we expect those estimates to bounce around as we sample over and over and over. If the standard error is high, that means that we expect there to be a lot of variation in those estimates from repeated sampling. That would mean we have a pretty low confidence that the one that we do have is close to the true value because there's just a lot of randomness to it if the standard error is high. If the standard error is low, that suggests that these don't move around very much, so there's a much higher chance that the one that we do have is close to the real value. Another way of saying this is that the standard error is an estimate of the standard deviation of beta hat, standard deviation being the tendency to move around randomly. And as I mentioned before, standard errors are generally going to go down as the sample size increases. So the bigger sample you have, the more precise the estimates. In the next video, this is going to be very important because we are going to use standard error when we conduct a hypothesis test.